Welcome to Things You Can't Live Without, the science podcast where I, material scientist Dr. Anna Pajajski, ask a special guest about the one thing that they can't live without. Despite us living for this stuff, we know that all of it has an impact on our planet. So together we'll find out from experts about the science behind the energy, materials, processes and people power that goes into making our favourite things exist, and what needs to be done so that we can continue making it all sustainably into the future. Joining me today is Dr. Hod Lipson, an author, speaker and researcher at Columbia University who works in the areas of artificial intelligence and robotics. Hod and his students love designing and building robots that do what you'd least expect robots to do: self-replicate, self-reflect, ask questions, and even be creative. Welcome, Hod, to Things You Can't Live Without.
My pleasure.
Really nice to meet you. So tell us, what is the one thing that you can't live without?
Well, the thing I cannot live without is a GPU. And probably you won't be able to live without one too.
So can you describe to us what a GPU looks like and what it does?
Well, a GPU is sort of like a computer, but it's really many computers stuck together into this enormous supercomputer. But it's something that's so compact you can actually carry around, put it in your desktop, you can put it in your phone, but it really underlies all of the AI revolution that we're seeing today.
Fantastic. And to take us through what Hod's GPU is made out of and how it came to be, we're also joined by Rio Tinto's Chief Executive of Minerals, Sinead Kaufman. Welcome, Sinead.
Hello, thanks, Anna.
Really nice to have you here. Can't wait to talk to you more. But first, Hod, I want to turn to you. Our listeners will likely be listening to us today on some sort of device, probably a smartphone or a laptop. Are GPUs allowing this to happen?
So behind the scenes, GPUs are sort of, they underlie almost anything that involves AI, involves real-time processing. So there's a lot of history behind it. All started with gaming and things like that. But right now, it's sort of, it's really all the horsepower of computing and learning, machine learning, image processing. All of that is happening on GPUs. And the more GPUs, the larger, the faster they are, the more stuff you can do.
So we're surrounded by these things. We all will rely on them even if we don't realize it. How about you? How are you using them in your research, in your work?
So the beautiful thing about GPUs, and originally they were sort of intended for gaming. The G is there for graphics processing units. We use it for machine learning. So besides the use at home when I have a TV or a phone, we use it in the lab all day long, and we beg for these things to be bought. And if you look at what, the bottleneck that's preventing big companies from becoming even bigger, the OpenAIs and the Googles, it's access to GPU. It's also one of the biggest consumer of electricity. It's one of the biggest, there's materials involved that are hard to get.
Can you paint us a picture maybe of the sorts of applications that you're working on in robotics?
Sort of things that I would say in the past, people thought were impossible for computers to do, like be creative. It was almost an oxymoron to say that a machine could be creative. But now we're seeing generative design everywhere, and it's growing in capacity and capability. And that's the kind of thing we work on. We work on making machines that can design things, AI that can design, make engineering designs, not just write poems, but design antennas and robots and things like that. But we also, in particular, recently work on this big question of self-awareness. Can robots be self-aware? Can robots be conscious? Can robots have feelings? And I know it sounds fantastical. I think it's around the corner, and underlying all of that is a huge amount of computation.
Has that been the limit so far, the computational power?
Oddly enough, it's I don't know if it's the limit. It's certainly a necessary ingredient. And without having a lot of computing power, you cannot get to these, very interesting levels of intelligence, of machine intelligence that are involved in things like creativity and self-awareness. These are sort of almost the holy grails of of machine learning, if you like. And they definitely involve a lot of computing power. Now, it doesn't mean that just a lot of computing power and we're done. There's a lot more to it.
Can you give us maybe one example of your favorite robot that you've developed, or a kind of interesting story? Any surprises?
Yeah, well, we are just now building a robot that it's a humanoid face. It's a soft face, and it's learning to make facial expressions that are sort of meaningful to people. It's learning, and in particular, what I've learned, we're trying to do right now is really hard. If we're trying to get the robot to lip sync, and in other words, it's trying to get the robot to move its lips while it talks, to smile like you are smiling right now, and to nod, and to look you in the eyes when it's talking, and to sort of make the appropriate faces at the right times. This turns out to be an incredibly difficult challenge because we have so many muscles in our face. Our face is so expressive. I have to say, I'm a jaded roboticist. I don't get excited by robots, but when this robot smiles at me, I smile back. I mean, it's very powerful.
I love that. And so this is what we mean when we talk about machine learning. It's about giving it inputs that it can, as you say, sort of teach itself based on, in this case, visual cues of how to move and how to react. Exactly.
It's getting a little bit less uncanny, I have to tell you. It's getting real. Pros and cons to this, we can debate, but it's definitely underlying all of that is the ability of this robot. It's far too complex for anything that we could program. So we just let this robot watch itself in the mirror, and then it watches YouTube all day long. And as it's watching itself and watching YouTube, it's gradually learning how to make authentic facial expressions, including some bad ones. It's learning to eye roll. It's learning to do some things that we don't want it to learn, but it's a lot better than anything we could program. So that's my surprise of the week, but really it happens all the time. And of course, the next thing we'll listen to the conversation and learn, when is appropriate to make a particular gesture based on the context of a conversation, and a lot harder to do, and likely will involve even more GPUs. Behind the scenes, we actually have to put these GPUs inside the robot, because inside the robot's head, because it has to have all that computation in real time as it moves around, because it needs to sort of process it right there and then.
And to take us through what Hod's GPU is made out of and how it came to be, we're also joined by Rio Tinto's Chief Executive of Minerals, Sinead Kaufman. Very warm welcome to the podcast, Sinead.
Thanks, Anna. Hi, Hod. Nice to meet you both.
Lovely to have you here. Of course, none of our computing world would be possible without the physical materials to operate it on. Hod, do you know, or can you make any guesses, of what materials your GPU is actually made out of?
Well, I know it's made of silicone. That's kind of what silicon underlies a lot of the semiconductors. But I have to say, beyond that, I am pretty clueless.
It's a very good guess. Yeah, silicon is definitely at the heart of your GPU. The stuff of computers are really the integrated circuits, or the computer chips. These are the small objects that contain the billions of electrical components like transistors and resistors and capacitors that do the actual calculations. And the main material of computer chips, as you say, is silicon. Silicon is what we call a semiconductor. The super clever thing about semiconductors and why we use them in electronics is that you can do clever things about changing their electrical conductivity in useful ways by introducing impurities, which allow us to create these tiny, tiny electrical circuits in a process called doping, which is another strange materials word. All of this is to say that you can kind of put these different flavors of silicon in different patterns on a computer chip. Because we can make these patterns of different flavored silicon on very, very, very tiny scales now, we can fit, as I said, billions of components on one very small chip. And you can do different layers of them so that in a very small volume, you can create an object that can have a huge amount of computing power. To summarize then, we've got, yes, silicon, definitely. Lots of different other elements from the periodic table, though, that we rely on for computing power as well, like phosphorus, antimony, arsenic, aluminium, gallium, indium, and boron. And it's the last of these, it's boron, that I want to talk to you two about today. I'd love to bring you in at this point, Sinead, to tell us more about boron. It's a very, very common material element in our lives, but most of us haven't really thought much about it. So can you tell us first, what actually is boron?
Yeah, certainly. It is a really interesting material. And when you ask people about what's mined, even within our own business, a lot of people don't really understand what boron is for. But I've got to say, boron is anything but boring. It's in absolutely everything. And the geology you need to create boron is a combination of an inland lake or a river where material can get deposited. So you need volcanics, you need faults, and you need a body of water. So not that common to have in one location. So if you think about where boron deposits occur in Turkey, in zones where there's mountains, at the San Andreas Fault in California, in Tibet, and also in Chile. When we look at research and development, where else can it be used? It is in everything. It's in everything from micronutrients in soil to help grow plants, to GPUs to help stability of a GPU, to the hardened glass on your iPhone or your iPad, and even that glass that bends on Samsung phones. It's one of the key components that helps that flexibility. But it's also in surfboards, it's in ceramics, it's in an incredible amount of things. We all carry it in our bodies. Most humans need about 2 milligrams a day of boron to help absorb vitamin D, to help manage hormone regulation in the body. And also we have it in things like our kitchens, where it's in Pyrex or sort of heat-resistant glass. It'll be in the oven glass if you're looking inside your oven when you're cooking something. When it is used in pyrotechnics, it produces the bright green color in fireworks. But if it's absorbed into carbon in diamonds, it makes blue diamonds, which are the rarest diamonds in the world. And so it really does exist around us in lots of different ways. So it's one of the most versatile minerals that I think we've ever seen in industrial use. I always refer to it as the WD-40 of the world. It's kind of really useful. And one piece that I found really interesting is it's also a neutron absorber. In things like the Chernobyl nuclear disaster, one of the things they did to slow the reaction down was to actually dump large amounts of boron into the reactor from the air.
That's incredible. I had no idea that it was used in so many different applications, but never really on its own. It sounds like it's often tied up inside other materials like glasses and ceramics.
Yeah, that's correct. And I was thinking, Hod, as you're speaking about how many GPUs I have even in the room I'm in, let alone in my house, it suddenly makes me think.
Can you take us a little bit more through that history?
The original mining that was done of boron going back to sort of 4,000 years ago was actually in Tibet when it was mined out of a lake. And at that point, it was used as a material to help with goldsmiths and silversmiths. And so its first uses were very much around it's got quite a high melting point. So it's used in things where you need to have a material that can help to be a medium. And it's used in applications where high heat and differences in temperature are critical, like the space shuttle tiles that are used for re-entry or for putting something in an oven, whether it's a domestic oven or an industrial oven.
So I'm wondering, it's interesting that you say that it's been used for a long time. In what form does it show up? Is it like a salt, like I'm imagining sort of granular material? Is it a liquid? How do you isolate it? And how much does it cost? Is this like gold? Is this something that you can carry around, or is it always tied into something else?
In its own right, it looks like a really boring brown sort of powder once it's processed. But essentially, it appears in rock or in salt. And essentially, what we do is we dissolve the rocks around it to be able to extract it in an acid form. Typically, as technology improves, then we can start to see, well, what other uses does it have? We've identified in the last sort of modern history that it's also one of the key components you can use to make ceramic, Kevlar type materials to protect equipment and people. And so the question is, what next? And when I hear you, Hod, talk about how you can actually generate not just an emotional computer, or one that understands and can generate its own feelings, but one that can generate feelings in humans as well and have that connection. And I'm thinking about our iconic mine in California, thinking, I don't think anyone on site is thinking that this material is going to help us to connect with machines better. It sort of takes us from the realm of what we used to think of as science fiction into science, and how materials can do that is actually quite a humbling thought.
You know, what I'm thinking when you talk is about how difficult it is to understand how to use materials. I mean, it's so unintuitive. You know, I think this is something that I'm seeing a lot when we talk about AI and creativity. Most people think, when they think about generative AI, that's everywhere these days, they think about AI that can write poems and generate movies and generate art. But where creativity is really needed is actually in areas like material science. This is where we humans don't have a lot of intuition. You know, it's so hard it's very few people, very few material scientists that can sort of anticipate all these uses of boron, for example. It's not something that you can just dream up. You really have to do a lot of experimentation to start getting real deep intuition. And yet, you show these kinds of things to AI, and for AI, understanding how do you generate new materials. In fact, it's easier for AI to generate new materials than to write Shakespeare, because Shakespeare involves all kinds of human quirks, but materials are very functional and well-defined.
Yeah, super exciting.
Maybe one example to give on that is one of our challenges in mining is always to make sure that we can sustainably find materials that we will need for the future. And what's a little bit terrifying as a geologist is that I think that AI might be better at this than we are. We had an example in the last few years where we found a copper deposit in a part of Western Australia which had been explored before. It was viewed as being essentially there is nothing there. It's got really deep sand. And we used computer-based technologies to actually identify the patterns around what could be there. In our first drill hole, we found a copper deposit. So I think as we think as a society, how do you generate these new uses of technology? Technology in itself is helping us find the raw materials that we need to be able to do the technology development.
So, Hod, on this podcast, I often like to transport my guests to a nightmarish future in which their objects can no longer be sustainably made. The materials can't be sustainably mined or sourced, or we've simply run out of them. And in that case, let's say that we don't have a future with boron in it. What are we going to do? What would your world look like?
The bad news is we'll go back to sort of where we were with computers in the 90s, or you know, when we thought we had fast computers, but we didn't know what fast really meant. So I think that's the sort of one scenario. But what's really going to happen is we're going to power up the GPUs that we still have with boron, and we're going to run the new AI to find some alternative. And I'm sure there's some alternative. You know, many times these materials, these minerals are replaceable. There are they're found by accident, and it seems to work, and we build a whole industry around them. But there's actually alternatives that might be better. Again, it boils down frequently to just the range of possibility when it comes to combinations of materials is so vast that it's just hard to understand what's out there and what's possible.
You're an optimist. I love this about you, Hod. That's a really nice answer. Sinead, we've already touched on this already, but would you call boron a particularly finite resource? You know, what are the risks that we're actually going to run out of it?
So being an exploration geologist by nature, I'm an optimist as well. And I think as you were asking that question to Hod, my thought was, well, we might need AI actually to think about how you can not just find more uses, but also explore for more. And I think I often, when we look at minerals that we use today versus materials that were critical in the past, you know, an example would be tin was a mineral that was, you know, so important when it came to industrialization in the early days. And yet now it's something, when you look at tin tantalum deposits, that's where lithium is often found as well. And previously, a lot of old mines in, say, Western Australia are now lithium mines. And what was the primary product of tin has become the byproduct. whereas lithium, which didn't have any value, has become the main product. And I think for boron, we're actually finding now that boron is also a material that occurs in nature, often associated with lithium, partly because it's generated in the same sort of processes with volcanic processes, use of brines. And two examples I'd give. One is that we discovered a lithium deposit in Serbia about 20 years ago in Rio Tinto, and it took us years to figure out what it actually was, because we were looking for boron. And we found lithium, but we found material that the world had never seen before. And so that's called jadarite. I'm a firm believer that even though exploration geologists have explored most of the world many, many times through different means, they always find something new when they go back and look at different patterns using AI, when they look at different technologies to be able to see what is beneath the earth. So I don't think we've run out just yet, but I think as we find more uses, we've got to keep pace in helping some of that technology to actually find more materials as well.
Hod, what happens to your computer components after you're done with them? Do you have a sort of robot graveyard in the corner of the lab?
Oh, wow. It's a great question. So we actually have a project which we call Robot Metabolism, which is all about robots that eat other robots. All right. So, okay. What does that mean? So this is a big name, but what it really means is imagine a robot that walks up to another robot and can take it apart and use its parts to make itself bigger or more capable or to repair itself and so forth. So we humans, we do this all the time. We eat chicken and we eat plants, and the plants eventually eat us, and we all consume each other. And in nature, we're all recycling all the time. It's because we're made of the same relatively small set of amino acids from which all of life is made. And that modularity, if you like, allows us to keep on reusing the same material over and over again for billions of years, literally. So I know it sounds nightmarish. It's the beginning of a horror movie, but really it's about creating a sustainable ecology of robotics.
That is a really fascinating vision for the future. For you, Sinead, what are the biggest challenges that you're facing to make sure that we can continue filling our digital world and otherwise with boron?
So I think there's probably two, and the mining industry is not a particularly well-regarded or popular industry, and a lot of concerns that we share with society is around how do we mine things with an environmental and social risk component to it, and make sure that we can do that in a sustainable way. And there's a legacy that's not that positive sometimes of mining. And how do we turn that into something that we can use in a way that that creates a mining of the future that is sustainable?
Well, just this discussion makes me wonder what other secret materials, secret ingredients are sort of underlying a lot of the things we take for granted, especially in this computing world. So boron is clearly one of them. What's the next in line?
It's a good question. I'm not sure.
I was working as a mine operator, and I spent some time doing a really basic course on computer science. I don't think I'd ever imagined that the difference today is computer scientists or governments or manufacturers of cars or computers are coming back to the mining industry saying, what exactly is in these components and where are they found? And nobody was asking the question about supply chains or sustainability of material. So I do think it's a really great question to ask, Hod, is what else is in there, or what was mined and why, and one of the materials we don't think have any use today. And has anyone actually asked the question of what could they do? So what is the next boron that's out there?
Yeah, super interesting. Thank you. So boron, as we've heard, certainly has a place in our future, and hopefully a sustainable future at that. Thank you both so much for taking us through the boron in your lives, Sinead Kaufman and Hod Lipson. Thanks for coming on.
Thank you.
Thank you.
You can listen to more episodes of Things You Can't Live Without wherever you get your podcasts. And don't forget to follow, rate and review us to make sure that you don't miss an episode.